welcome to this video. In this video, we are going to talk about the most important classification in chemistry. The most important classification in chemistry is the periodic table. The periodic table is very important in chemistry because the entirety of chemistry is built on the elements in the periodic table. So that is why we have to understand how the periodic table works, the characteristics of the periodic table, and how it is being used on a daily basis to achieve some breakthroughs in chemistry. Now, the periodic table. The most important classification in chemistry is the arrangement of the elements in the periodic table. In 1869, Dmitry Mendeleev, a Russian scientist, constructed the periodic table by arranging the elements in the order of their increasing relative atomic masses. From this arrangement, elements with similar properties kept recurring at regular intervals or periods. Now, you see, a lot of scientists made some attempts to arrange elements together. Some of them just classified all the elements into metals and non-metals. That was by Lavoisier. But in 1869, there was this brilliant Russian scientist that was able to construct the periodic table. Now, the periodic table is simply a table showing all the elements in chemistry, the atomic numbers, the atomic masses, and other properties of those elements, like electronegativity. That's what periodic table is all about. The periodic table is just a table. It's like a table that you can draw on the board. I'm still going to draw it on the board anyways. It's like a table. It's a table majorly that contains all the elements in chemistry, all the elements that have been discovered so far, or the ones that have been synthesized in the laboratory. So, in 1869, this Russian scientist called Dmitry Mendeleev was the first person to arrange the elements on the periodic table according to their relative atomic masses, RAM. Mendeleev arranged the elements according to their atomic masses. And when he was arranging those elements according to their atomic masses, he realized that some elements kept recurring. Some elements with similar properties, they kept recurring at intervals or at periods. Those elements that kept recurring at intervals were having similar chemical properties. And then Dmitry Mendeleev, of course, he noticed that, and then, but there were some elements that were not discovered during his time. Elements like gallium, scandium, germanium, they were not discovered during Dmitry Mendeleev's time. So what did Dmitry Mendeleev do? Dmitry Mendeleev left some gaps for those elements that have not been discovered during his time. He even predicted the properties of these elements. Later, elements such as scandium, gallium, germanium, etc. were discovered. These elements fitted into the gaps left by Mendeleev and even had the predicted properties. However, with the discovery of the electronic structure of the atoms, it was realized that elements vary regularly with their atomic number and not atomic masses as suggested by Mendeleev. This discovery led to the modern periodic law. So, when Dmitry Mendeleev was arranging the elements on the periodic table, he saw that there should be some gaps somewhere because those elements have not been discovered yet during his time. So he left the spaces for those gaps, for those elements rather. He left the spaces or the gaps for those elements that were not discovered during his time. And he didn't just leave the spaces, he even predicted the possible properties of those elements that were not discovered. He predicted their properties. And later on, after about some years later, those elements that were not discovered during Dimitri Mendeleev's time were eventually discovered. Elements like scandium, like germanium, like gallium, they were eventually discovered. And when they were discovered, they had the predicted properties that Mendeleev had suggested about them. They had the predicted properties. They also fitted into those spaces, into those gaps that Dmitry Mendeleev left on the periodic table. They fitted into those gaps. And then we see that what we have today now is a complete version of the periodic table. Now, there was a minor mistake when the arrangement was done. This minor mistake was this. Dmitry Mendeleev arranged the elements according to their relative atomic masses. He used the atomic masses to arrange the elements. But later, when scientists discovered electronic configuration, which we are still going to talk about, with the discovery of electronic configuration, it was later realized that the elements were not supposed to be according to their atomic masses, but they vary according to their atomic numbers, not atomic masses. So the elements on the periodic table, yes, they vary. Yes, they are properly arranged, but they are arranged according to their atomic number. This discovery led to what we call the modern periodic law. The modern periodic law. And what is the modern periodic law? The modern periodic law states that the properties of the elements are a periodic function of their atomic numbers. That is the modern periodic law. I'll take that again. The modern periodic law states that the properties of the elements are a periodic function of their atomic numbers. So that is the modern periodic law. Before the modern periodic law was discovered, the periodic law that Mendeleev used was the one that people knew then. And what was that periodic law that Mendeleev used? It's still similar to this, but what Mendeleev used was that the Mendeleev's periodic law it states that the properties of the elements are a periodic function of their atomic masses. That's the one Mendeleev used because he arranged the elements according to their masses. So that Mendeleev periodic law was the properties of elements are what? The properties of elements are a periodic function of their atomic masses. That's Mendeleev's periodic law. But with the discovery of electronic configuration is just simply the way you arrange electrons around an atom. The way you arrange electrons around an atom is called electronic configuration, and we are still going to discuss that. So, with the discovery of electronic configuration, it became clear that it is not according to the atomic mass, but according to the atomic number. It is not according to the atomic masses rather, but according to the atomic numbers. So that is what gave rise to the modern periodic law, which I'm going to say one more time. The modern periodic law states that the properties of the elements are a periodic function of the atomic numbers, meaning that all the elements are arranged periodically according to their atomic numbers, not according to their atomic masses. Now, the next thing we are going to talk about is the electronic configuration of atoms. The electronic configuration of atoms. What is the meaning of electronic configuration? The electronic configuration of atoms is the arrangement of electrons around the nucleus of the atom of an element. So when you talk about electronic configuration, we are simply looking at how electrons are arranged around the nucleus of that atom. Because you see, An atom has three fundamental particles. An atom has three fundamental particles. And these three fundamental particles are protons, neutrons, electrons. The three fundamental particles of an atom are protons, neutrons, and electrons. Now you see the protons and the neutrons, they are inside the nucleus of the atom. The nucleus of the atom is the center of the atom. The nucleus of the atom is the center of the atom. So the protons and the neutrons, they are packed inside the nucleus of the atom. But the electrons are not inside the nucleus. The electrons are moving around the nucleus. So electrons revolve around the nucleus of an atom while the protons and neutrons are packed within the nucleus of the atom. Now, the protons are positively charged, meaning that they have a positive charge. The electrons are negatively charged, meaning that they have a negative charge. But the neutrons, they don't have any charge. The neutrons are neutral. They don't have positive charge. They don't have negative charge. They are electrically neutral. So the protons are positively charged, electrons are negatively charged, while neutrons are electrically neutral, meaning that they have no charge. They have no charge. Another thing I want to let you know is that the number of protons in an atom is referred to as the atomic number of that atom. I will say that again. I didn't write that on the board, but I'm going to say it again. The number of protons that an atom has is the atomic number of the atom. So which means that if an element has, let's say, like 5 protons, if an atom has 5 protons, it means that the atomic number of that element is 5. Or if an atom has, let's say, 28 protons, if an atom has 28 protons, that is 28 protons are inside the nucleus of that atom. If an atom has 28 protons, it means that the atomic number of that atom or of that element is 28, because the proton number is also known as the atomic number. Don't forget that. The proton number is also known as the atomic number. But there is something else I want you to think about. If an atom has, let's say, 28 protons and it also has 28 electrons, I'm going to say that again. If an atom has 28 protons and it also has 28 electrons, what do you think will be the total charge on that atom? What should be the total charge on the atom? Now, listen. You know that protons are positively charged, that is, they have positive charges. Electrons, they have negative charges. So if an atom has 28 protons, that means it has 28 positive charges. And if that same atom has 28 electrons, it means it has 28 negative charges. So 28 positive charges and 28 negative charges, by the time you bring them together, what happens? They will eventually cross out each other, meaning that plus will cancel minus, plus will cancel minus. And if you have 28 of pluses with 28 of minuses, they will eventually cancel each other, meaning there won't be any charge left on that atom. So that means that if an atom has equal number of protons and electrons, then that atom is neutral. I'll take that again. If an atom has equal number of protons and electrons, it simply means that that atom is neutral, because the protons and the electrons, I'm talking about the charges. The charges on the protons and the charges of the electrons, they will eventually cross out each other, leaving the atom to be neutral. But okay, what about if you have more protons than electrons? Let's say that you have like 30 protons and you still have 28 electrons. It's possible to have that. You could have 30 protons and 28 electrons. Now look at it. 30 protons, that means you have 30 positive charges. 28 electrons, that means you have 28 negative charges. So 30 charges and 28 charges. What is 30 minus 28? That's 2, isn't it? That means you have two positive charges left if they should cancel each other. If the protons or if the charges should cancel each other, that is, if the positive charges and the negative charges should cross out each other, you will still be having two positive charges left because you have 30 protons and you have 28 electrons. So you will still have two more positive charges left. You still have two more positive charges left. And because you have two positive charges left, it means that that atom is a positive atom. It is a positively charged atom. A positively charged atom is also known as a cation. It's called a cation. I'm still going to write all these things on the board, but you have to know them before we even start looking at the electronic configuration. So, okay, what about if you now have you still have your 30 protons, but this time around you don't have 28 electrons. You have, let us say, 35 electrons. You have 30 protons and 35 electrons. Now, if the 30 protons and the 35 electrons should cross out each other, you would realize that you will still be having 5 more electrons left. So 30 protons, that's 30 positive charges. 35 electrons, so that should be 35 negative charges. So 30 charges, 30 positive charges, 35 negative charges. If you bring them together, if positive cancels negative, then you are going to have 5 more electrons left. And because you have 5 more electrons left, it means that that atom is a negative charge because you have negative charges left. So that atom is definitely a negative charge. And what do we call an atom that is a negatively charged atom? We call it an anion. Anion. A-N-I-O-N. Anion. So if it is positive charge, it is cation. If it is negative charge, it is anion. So we are still going to discuss this one more time. Now, let me come back to electronic configuration. There are different ways of writing the electronic configuration of atoms. There are different ways you can write electronic configuration. There is not, it is not only one method that you can use. You have several methods, which we are still going to discuss. Now, out of those several methods, the number one method that is very popular is using the KLMN shell. That is the first method I'm going to discuss with you. That is, you are using the KLMN shell configuration. See, this K stands for a letter. It's not, it stands for a shell rather. It represents a shell. It's just like a labeling. It does not really stand for a name or anything. It is just the label for that shell. A shell is the path through which electron travels around the nucleus. So let's look at it. Using the K element shell, electrons revolve around the nucleus in spherical regions. Yes, electrons don't just gyrate around the nucleus, they are going in a specific manner around the nucleus. So assuming that this is the nucleus, my hand, my fist is the nucleus, then electrons are moving around this nucleus in a spherical manner, in a circular manner. They are moving around. This is the nucleus already of the atom. So the electrons are now circling it. They are circling the nucleus. That is in the spherical region. And those circles. What do we call those circles? We call them shells. We can call those circles. That is those circles through which electrons are moving around the nucleus. Those circles that they are moving with, they are on the circle, they are moving around the circle. We call those circles shells, or you can also call them energy levels. I'm still going to draw them on the board. Energy levels, or you can even call them orbitals. So that means they have three names. You can call it shell, you can call it orbital. Orbital is spelled O-R-B-I-T-A-L, orbital. Then you can also call it a energy level. So the spherical regions called shells or energy levels, which are situated at various distances from the nucleus. The radius of each shell from the nucleus is specific. Electrons in the closest shells to the nucleus have less energy than those farther away from the nucleus. Starting from the shell nearest to the nucleus, the shells are labeled as K, L, M, N, O, P, etc. That is, it's just labeling. It's not as if the K stands for anything. It's just like an alphabetical letter. I'm going to explain that one more time. They have energy levels numbered 1, 2, 3, 4, 5, 6, etc. The maximum possible number of electrons in a shell is given by the formula 2n squared, where n is the energy level number of the shell. So what we are saying here, or what I am trying to let you know, is that the nucleus is the center of the atom. The first circle around that nucleus is the K shell. The second circle is the L shell. The third circle is the M shell. It goes on and on like that. So the shell that is very close to the nucleus can only accommodate a certain number of electrons. Each shell can accommodate a certain number of electrons. They have their limits. Each shell has its limits. So each shell can only accommodate a certain number of electrons. For instance, this K shell, for instance, that's the very first shell. That's the shell that is the closest to the nucleus. This K shell can only take 2 electrons maximum. It cannot take beyond 2 electrons. And there is a reason for that, which we are still going to talk about. The K shell can only take 2 electrons. The L shell, that's the next one, it can only take 8 electrons. You can't go beyond 8. You can go less than 8, but you can't go beyond 8. That's the way the electrons have been arranged in the atom. The maximum number of electrons on the L shell is 8. It can't take more than 8. So the first shell now is K shell, the second shell is L, the third one is M, it goes on like that. Now this K shell, it has an energy level of 1 because it's the first shell. That's the first shell, so it has an energy level of what? Of 1. The L shell has an energy level of 2. The M shell has an energy level of 3. Let me tease your brain. What do you think this P shell, what will be the energy level of P shell? What do you think the energy level of P shell should be? Let's count together. This is 1, 2, 3, 4, 5, 6. So that means that the energy level for P is 6. Now, energy level is different from number of electrons. Energy level is just telling you which shell you are talking about. Are you talking about the first shell? Are you talking about the second shell? Are you talking about the third shell? That's the energy level I'm referring to. It is completely different from the number of electrons that can stay on each shell. Do you understand that? Now, for the number of electrons that can stay on each shell, there is a formula for it. And that formula is 2 times n raised to power 2. I'll take that again in case you can't see it from the camera because I know that my camera is not really too good. I'm just managing it. 2 times n raised to power 2. That's 2n squared. 2n squared is the formula for the maximum number of electrons that can stay on a shell. That n is the energy level I'm talking about. N, small letter n, represents the energy level that we are talking about. So if I ask you, what is the formula you are going to use to get the maximum number of electrons that can stay on a shell? The formula is 2n raised to power 2. N represents the energy level. That is what shell number are we discussing? That's what N represents. So if we are talking about M shell, for instance, M will be taking energy level 3. So if I use this formula, that will be 2 times 3 squared. And what is 3 squared? That's 9. So 2 times 9 is 18. So that means that on the M shell, the maximum number of electrons that can stay on M shell is 18. Is 18. Now, what about for the first shell, which is K? If I take K as my energy, as my shell, the energy level is 1 because that's the first shell. The energy level is 1, so that will be 2 times 1 squared. 1 squared is still 1, and 2 times 1 is 2. So that means that the maximum number of electrons that can stay on the K shell is 2. I'm still going to analyze all this. I'll rub off the board now, and I'll still analyze again so that you can get the simple mathematics behind it. And then from there, you can now draw out the atomic structure of that element. Now, let us look at the maximum number of electrons that can stay on the K, L, M, N, O, P, Q, and so on and so forth shells. We want to calculate it together. So let's start with the very first shell. The very first shell is the K shell. And the K shell, because it's the first one, the energy level is number 1. That's number 1. That's for the K shell. Now, what will be the maximum number of electrons that can stay on the K shell? Now, since n is 1, the formula to use is 2n squared, that is 2 times n raised to the power 2. That's the formula to use. So, since n is 1, I'm going to substitute 1 into this formula. So, that means I'll be having 2n squared will be equal to 2 times 1 squared. Now what I'm going to have, I'm just substituting the value of n into the formula, which is 1. So what is 1 squared? 1 squared is 1, of course. So that will be 2 times 1, and 2 times 1 is 2. So that means that the number of electrons, the maximum number of electrons that can stay on the K shell is 2. That's the maximum number of electrons we can have on the K shell. The K shell can only accommodate a maximum number of 2 electrons. And when it reaches that 2 electrons, when it accommodates exactly 2 electrons, we call it a duplet configuration. Duplet, D-U-P-L-E-T, duplet. We call it a duplet configuration. A duplet configuration. So duplet means that there are 2 electrons on the K shell. That's what it means. Now, let us go to the next shell. Let us go to the L shell. That's the next one, L. So, since L is number 2, the energy level 2 is 2. Then following the formula, so I have 2n squared, but this time around my n is 2. So I'm going to write 2 times 2 raised to power 2, and that gives me what? What's 2 raised to power 2? That's 4. So that's going to be 2 times 4, and that gives me 8. So that means that the maximum number of electrons that can stay on the L shell is 8. That's the maximum number of electrons. Then we'll go to the next one, which is the M shell. M is the third shell, so the energy level is number 3. So I'm following the formula again, the same formula, 2n squared, which is going to be, my n is 3 this time around, so it's going to be 2 times 3 raised to power 2, and that gives me 2 times, what is 3 squared? 3 squared is 3 times 3, and that's 9. And 2 times 9 is what? 18. So that means the maximum number of electrons that can stay on the M shell is 18. Then after that, we'll go to the next one, to the N shell. To the N shell, the energy level is 4. And then following the formula again, that will be 2n raised to power 2. That's 2 times 4 raised to power 2. So that's going to give us 2 times, what is 4 raised to power 2? 4 raised to power 2 is 16. That's 16. And 2 times 16 will give us 32. So the maximum number of electrons on the N shell, on the N shell is 32. Then moving to the O shell, the same principle, that's 5. And so if I follow that formula, that's 2n squared, and that's 2 times 5 raised to power 2. 5 raised to power 2 is 25. So that means I have 2 times 25, and that gives me 50. I can keep going on and on and on like that. It's still the same principle. P, which is 6, and this is 2n raised to power 2, which is 2 times 6 raised to power 2, and that's 2 times, what's 6 raised to power 2? That's 36. Times 36 gives us 72. So it goes on and on. If you have a Q, after P is what? It's Q, after Q is R, you can keep going on and on like that, and then these are the maximum number of electrons that can stay on this shell. So for the K shell, the maximum number of electrons is 2. For the L shell, maximum number of electrons is 8. For the M shell, maximum number of electrons is 18. For the N shell, maximum is 32. For O, maximum is 50. And for P, maximum is 72. Now, there is a slight variation. For the first 20 elements, I'm going to say that one more time. For the first 20 elements, the maximum that can stay on M is 8. I'm going to say that again. For the first 20 elements, maximum number of electrons on the K shell is still 2. Maximum number of electrons on the L shell is still 8. But once we go to the M shell, for the first 20 elements of your periodic table, the maximum number of electrons that can stay on the M shell is 8. The maximum that can stay on the N shell is 8. Why is that so? It is so because when you start filling the orbitals, we're still going to use the Hund's principle. We are going to use the Hund's principle. You will see why that is so. When you start filling the orbitals, the energy level, the lowest energy levels must be filled first before they go to the highest energy level. That is, you fill up, when you want to fill a drum now, you don't fill the drum from the top, you fill the drum from the bottom. As you are pouring the water, the bottom gets filled, the water level gradually rises, right? It gradually rises till it gets filled to the top. The same thing is applicable to filling the orbitals. For the first 20 elements, you fill the lowest levels first before you go to the highest level. When I start drawing them, you know what I'm talking about. So that means for the first, so this is only applicable for the first 20 elements. So for the first 20 elements, maximum on the K is 2, on the L is 8, on the M is also 8, on the N is also 8, and the first 20 elements do not exceed the first 4 shells. They stop at the N shell. The first 20 elements only use K, L, M, N shells. That's the only shells you can get for the first 20 elements. So this is 2888 for the first 20 elements. Now, in the next video, I am going to start drawing out the atomic structures, and then we'll start filling up the shells together.